Okay, welcome back, guys. So this is where we left off. So let's begin the layout. As you can see, we already have DRC error about 15. So maybe let's focus on clearing the error first. Then we can now start the layout. We'll start the routing. By the way, to give you an idea of where we are right now, so let me bring up this design flow. So this is the design flow chart again. You start from the IC specification idea, then you move to the circuit level schematics and the electrical simulation. So we've done all of this, we've passed these first two stages. So currently, where are we now? We are in the physical design phase, that's the layout phase. So you can see now P cell based and netlist driven layout. So netlist driven layout is actually the last method we used. That method is called the last method we use is called netlist driven layout. The method of importing spice, it's called the netlist driven layout because we use the netlist. Remember, we had to come here and generate the netlist first, then we use the netlist that's been generated. So that's what the third method is called. But the second method is called PCL based layout. That's the method where we generated the devices from this feature. That's called PCL based layout. Why the other one? I don't know the name for it. Maybe that's, what should we call that one? That's long suffering based. Don't mind me, that's just joke. So that's just the material by material layout. So which would take time. So we're currently here. We're currently in the physical design phase, that's the layout phase, and we're still working on this. And let's say for now we are simultaneously working on this and this. So as we're doing the layout and the routing, because there's routing is the wiring of the layout, as we're doing that, we are at the same time checking for design rule checks and also design rule errors. So we can say we're doing this two simultaneously. There are many times you have to do this first, then you let Magic do the overall checking for you. So what am I trying to say? Though we're doing the rule check simultaneously, but when you don't, you also need to do the final rule check. So say we're here, these two, and after that we move to layout versus schematics, that's LVS. And so let's just get back to work. So like I said, let's reduce this DRC error. Let's try to reduce. So I suspect one of the reasons why we have these errors, one of the errors, is because these two guys are overlapping, they are too close. So let me zoom in a little. Okay, I think this is the best we can get. So let me separate these guys. They are too near, so I think they're overlapping. You can see the area here too is gray, like it's giving this white dotted area. So it means there's error here. So one of it could just be that because they're overlapping the two transistors. So you press the I button on your keyboard for selection of cells. Then I want to move it to this point, so I move my cursor there and I press the M button. So you can see from, I think, 19 it's been reduced, or is it 15? It's been reduced to just 10. So the remaining 10, let's try to zoom in. So we're here, zoomed in, so we have white areas here, and let's ask DRC why do we have error there. So again, you try to make a box that will fit that area of the error, then you come down to the to the command windows and say and type drcy, and it says the metal minimum area is less than this. The second reason is that the metal spacing is less than this. So one of the rules, I think one of the rules for this technology, for the fabrication, so that the fabrication will go on well smoothly, you need to follow these rules. And I think one of the rules is the meta one is this blue layer. So you have it here also. Says the area of the meta one is less than this value here. So that's the size here. So that is would have to increase. So it's too small to fabricate such like an area. So that means we have to increase the that area. And I think one of the ways to do that is actually to increase the gate length, because I think one of the reasons why this is small is because the gate length is small. By the way, the gate length is the length from this point to this point. That's this length, this horizontal length, like the way I'm moving the cursor this way. That's the gate length. So you can see that maybe if the gate length was longer, then this area too would have, this contact area would have been wider too. So I think one of the maybe solution to it is to increase the length, like I told you, and that's because I told you that the length, I talked about the length that the Magic VLSI 2 may complain about it. So yeah, we can now see the error is popping up. And another, it says the spacing of the metal, maybe it's too near to the nearest metal layer, maybe between these two layers it's too near. So we have to work on that also. I think let's check what the error 2 here is too. So DRCY, this one just says the spacing is less than 0.2. So maybe this metal 1 and this adjacent metal 1, their minimum distance, it's less than 0.23, and we can confirm that. So let's just quickly do that. Let's increase the grid size to what is measurable. So currently is in 0.1. So 0.1, then let's count the boxes. So this is 1, starting from here, 1, 2, and then the third box has the metal layer of this other one starting. So we can just say roughly that's this one full box, then this like half box, so that's 0.1, 0.15, then this even not even up to half. So indeed it is less than, this spacing between them is less than 0.23. So again, had it been we make the length longer, I think it will also help this spacing issue. So, and definitely if we go to the other transistor, by the way, do we recognize these transistors? So remember these NMOS, why? The diffusion, you can use the diffusion is usually green, the drain and source is, you use the N diffusion, so it's green color, so N diffusion. Why the PMOS, this is the PMOS, look at the drain. So this is the gate, so this is the drain and the source, you get. So, or you can call them either, whether the source, the drain, the diffusion is blue. So that's, I'm sorry, it's not blue. Blue is the metal layer, the contact of the diffusion, but the diffusion is beneath the contact, which is what? Brown. So brown for diffusion, it's P diffusion. So that's PMOS, you get. So let's take note, let's learn to identify devices. So this is the NMOS, this is the PMOS. So let's see if there's any error for the PMOS. It seems there's error also. You can see the error is around the gates. So you can see I talked about the gate length. So definitely that means the solution to this error is just go and increase the gate length. So how do we do that? Since we used the netlist driven the netlist based generation to get these devices here, so let's go back and change the netlist and come back here again and regenerate. So I'll go back to a scheme and I'll change the length of, they have the same length, I'll just change the length. I'm not going to touch their width. So to still make things the way it is, I'll just increase the length, and it's the same length I'll give to them. So that way, while the performance we got would not be affected. So I'll just double click. This is the NMOS. Like I said, for Skywater, 0.5 it's fine, because it's about 130 nanometer and the minimum length is 150. That's 0.15. So 0.5 it's fine. But for the global foundries, it's 180 nanometer, but the minimum length, I told you all those 180 130, they are naming gimmicks. They are supposed to mean the lowest, the minimum length that is fabricatable, but it's not usually the case. Sky 130 is 130, right? But it's actually 150 that is the minimum. Global foundry is 180, right? But I think it's usually 0.2, that's 200 nanometer. So, and 0.3 is so close to the minimum, so that's why it's not working. So what I'm going to do is I will just try to make it almost times, let's almost one micrometer. So I can do 0.8, because I discovered from that 0.8 the Magic VLSI2 usually don't have issues. That's the DRC checker usually don't have issues with 0.8 micrometer of length. Anything from 0.8 it's fine. So I'll do OK. Change for the NMOS also. So 0.8, remember they are the same length, so in order not to alter the overall performance and characteristics of the end of the inverter, you need to maintain what was before. So before they were the same length, so don't change the length, make them same length, because they were the same length before. And we're not altering the width, because we said the sizing, for the sizing we'll just be changing the width alone, so don't touch the width. So 0.8 for the length. Then I've made some changes, so I hit the Ctrl S button, hit Ctrl S, and yes, then regenerates the netlist. So generates the netlist again, and it's been generated and the changes are reflecting. Then I save. So what do? I go back to Magic again. We don't need these cells anymore, so we can just delete them. So to delete, delete would be it's a cell, right? Then you D, so I to select the cell, then D. So I don't know if it's seeing Magic is saying this all layers as a cell, but maybe just to be safe I can just delete them layer by layer, like this layer. So to select a layer is S, then D for delete, S, D for delete, S for select, D for delete, S for select, D for delete. So I'm done. Then I can now come back, file, because we're using the netlist driven layout method for this. So I'll come here, file, import the spice or the netlist. I look for the name of my spice, navigate to where it's been saved. Remember I told it's usually in this folder which is called the .scheme folder, which is usually in your home directory. So and this is the name of my spice netlist. So I would open. Okay, let's see what we have here. So it's all good, at least it's better than before, that the DRC error started with 19 or 15 errors, but now we just have 5 errors, and most likely I suspect the error would be from the fact that these two devices are overlapping. So let's just separate them. So to select I for selecting a cell, then I move my cursor to where I desire to move it to, then I press the M button, and yes, voila. So yeah, no more DRC error, so it's all fine. So next thing would move to routing. So routing is, if you want, it's just your what you may want to call wiring. So this is the PMOS, this is the NMOS, right? So, and this is the NMOS and this is the PMOS. By now you should be able to identify your PMOS, your NMOS. You can take the video back. I mentioned how to identify them. You use the diffusion layer, that's the source and drain. Then so the NMOS, the PMOS, then let's go back. They are being connected with some wires and all, so we need to do this connection. So that's your routing. So let's do the routing, and before that I would like to check the time. Okay, there's 16 minutes. Okay, so though for the now it's time to do the routing. There's what is called floor plan. Based on the floor plan, or let me say the floor plan affects how you want to arrange. So you may just want to leave them like this, NMOS, PMOS, or you may actually want to do them this way, arrange them this way, where you have the PMOS up and the NMOS. Anyhow, any orientation, you may want to make this horizontal, any orientation, but usually it's the floor planning that would guide the orientation. So floor planning is just the area of the IC, how big you want the IC to be. Usually you want a small area IC, so maybe you want the IC to just be as small as, let's say 3 millimeters square, for instance. So to do the floor plan, again you need the grid. You come here, let's use 0. Let's use 1 micrometer. So to do a 3 millimeter square floor planning, so each grid is, the dimension is micrometer. So how many micrometer makes millimeter? So I think that's about, is that 1,000? So that means you have it, you, by saying the floor plan is 3 millimeter, maybe then or let's just say 1 millimeter. So that means the floor plan will contain 1,000 of this, what is it called, these boxes. So that's really much, so you can see in the world of chip design, 3 millimeter square is really big. 1 millimeter square is really big, because everything is in micro. The dimension of all the materials are usually in micrometer. So let's say this is the area you want the whole design to cover, like the current area, that is, this area, just this area. So if this is the area you want the IC to cover, so that means all you need to do is either you want to count 1 2 3 4 5 6 7 8 9 10 11 12 13. So that's 13. Each box is their dimension is 1 micrometer. So that's 13 times 1, so that's 13 micrometer by whatever this is. So times that will be the area, but yes, you can't always be counting. So if you want to do the measurement, so I think the instruction is measure box, if I have not forgotten the instruction. Measure box, there's a command, let's see, Okay, let's do, okay, the command is, okay, B. So just come here, measure box, then it gives you the measurement of the box. So let's use the one in micrometer. So it's about 14 by 14 micrometer. That's the area, and yeah, I think I counted about 13 also. So it's 14 by 14. So but for now, we're not going to be bothering about floor plan and all. Floor plan, of course, it's just two. CMOS just contains two devices, so of course it's not going to take any. It's not going to take in much area. So floor plan does not really matter here. But maybe for big circuits, complex circuits, so you want to be placing limit on the floor plan so that you can find the optimum arrangement of each devices. So maybe for now, let's just focus on utilizing this area, just this area I have done by this box, so we can begin the routing. So I would continue in the next video.